Tatanchi, and I work with Communitech. I'm pleased to introduce today's speaker. Professor Pascal Poupart is a professor of machine learning in the David R. Sheridan School of Computer Science at the University of Waterloo. He is research director of the RBC Borealis AI Research Lab in Waterloo and serves as scientific advisor for Huawei Technologies and ProNavigator. He is also a member of the Waterloo AI Institute and the Vector Institute. Welcome, and welcome to all our online viewers.
Well, thank you very much. Okay, so it's an honor for me to be here, and then I've had a chance to interact with lots of people here at Communitech, so this is great. Are the folks from ProNav here, by any chance? Okay, well, that's fine. So in any case, yeah, that's one company that I've had good interactions with and that I serve as a scientific advisor for. But in any case, yeah, so I'm based at the University of Waterloo. I'm also a member of the Waterloo AI Institute, the Vector Institute, and as Kusha was saying, then I'm also a research director at Borealis AI. So let me just say a few more words about Borealis AI. So that's a new research institute that was started just recently. And then in particular, we're starting a research lab here in Waterloo. So we currently have 5 research centers, so Waterloo is one of them. And then in total, we currently have 70 researchers, so we're doing both fundamental and applied research. So this is a little bit different than other places that might focus mostly on the applied part. So, so the research is both, on the side of academic research, but also industrial research. So some of the topics that we're looking at are listed here. And then for 2019, our target is to actually grow to 160 researchers. So these are exciting times. Okay, now at the university, so I'm doing some research as well with a strong research group. So we have 4 main topics that we're currently looking into. So that includes deep learning, as well as reinforcement learning, natural language processing, and theory. So today, my talk is going to focus on 2 topics. The first one, transfer learning, which is within deep learning, and then also reinforcement learning. So I'll talk about some form of motion-oriented reinforcement learning. Okay, so this is for the core part of, like the technical part of my talk. But now let's take a step back, and then what I'll discuss is how, because we're entering a new era, and there's lots of excitements around some of the technologies that are emerging every day. What's interesting is that a lot of people are now suggesting that perhaps there's going to be a technological singularity coming soon. So I'll define this a bit more. I'll talk in particular about superintelligence, merging machines with human intelligence, and also self-evolving systems. But then to achieve these things, there are some challenges. And then so I'll talk about 3 important challenges and some of the research that I've been doing with respect specifically to the first and the second challenge. Okay, so this idea of singularity is not new. So in fact, if we go back to 1965, there was a mathematician of the name of Irvin John Good. He basically wrote a very interesting paper called Speculations Concerning the First Ultra-Intelligent Machines. And basically, he was already speculating that with computational tools, at some point, there could be an emergence of some new technologies that would essentially just run away on itself. Okay, so from his perspective, the idea is that computers would eventually lead to this superintelligence, and then this would lead to a technological boom, and then so it would lead to all kinds of things that we cannot think of at the moment. But then, in any case, there would be a singularity in that sense that there would be this technological boom. Okay, so now more recently, there's also Ray Kurzweil. So he's a computer scientist and also a futurist at Google. And then in this case, he's been predicting that there will be a technological singularity soon. So in fact, he wrote a book in 2005 saying that the singularity is near. And what he was really talking about, I guess there are 2 interesting arguments. So the first one is that he noticed that with technology, and when we look at human evolution, it always gets faster and faster and faster. And we could say that technological progress often follows an exponential curve. And then so from that perspective, you see, if we're at the present day here, often people make predictions into the future based on how things have evolved in the past, and then the rate in the past is always slower than the rate going forward. And then often we make some predictions that completely underestimate what will happen. And then it's this idea that often because we assume that the rate going forward is going to be the same as the rate in the past, and we're essentially making linear predictions, okay, but really we need to take into account the fact that one technology allows another technology, which allows another technology, and then from that perspective, often there's an exponential growth. And then so based on this, you see, he made this prediction that at some point, right, the technology again is going to enter some runaway period, and then it will lead to a singularity. Now, how is that possible? Because we're humans, we've got our own limits, right? So even if we come up with new technologies that allow us to do certain things better and faster and so on, I mean, physically, as humans, we are limited, right? So then his prediction is that, in fact, the singularity will happen when there's going to be a merger of machine intelligence and human intelligence. So the idea is that there's all this progress with respect to biotechnologies and so on, and then we can augment human intelligence and, in fact, augment our own physical limits with some technological advances, and then we'll be able to go beyond what we can physically do at the moment, and then that's how he predicts that there will be a singularity. Okay, so this is very interesting, but I guess, yeah, from a technological perspective, there are challenges. And let me also suggest another way of thinking about the singularity. So today, one topic that is very exciting, that has led to all kinds of breakthroughs, is machine learning. So here, why is machine learning leading in terms of many advances? It's this idea that traditionally with computers, the way we get them to do something is that we program them, right? So we write a set of instructions. So we have to essentially program them for pretty much every task, and then so we have to think through what the solution is going to be, and then from that perspective, there's some limits about what us as humans we can figure out in terms of complexity and how we can spell it to a computer. But now with machine learning, there's a new paradigm where instead of telling the computer directly, here's what you need to do, here are the instructions, what we do is we simply give some examples to a machine, and then we tell the machine now, figure out on your own what is the right thing that you should do. So what are the instructions that you should follow to essentially mimic what is in the examples. And then so concretely, if we look at machine translation, right, so there was a time decades ago where people were essentially writing down some rules about how you would do machine translation, let's say based on linguistics and so on, but this has changed a lot, and today the state of the art is that you simply provide corpora of text in two different languages that are aligned. These are examples, and then the machine essentially figures out how to map text from one language to another. And then the more data you feed it with, the better it gets at. And then nobody is spelling out what are the rules to follow to do machine translation. Essentially, we're programming now at a meta level where we've designed algorithms that can essentially learn what are the instructions that should be followed. And then, so this is how now you see there's a new wave of progress that's possible because of this. Another example would be in computer vision. So there too, historically, we had a lot of trouble to just take an image and then write down some instructions that would essentially tell the computer, here's how you recognize a car or a person or a different type of object. And instead, what we do is we simply label the different things that we would like the computer to recognize, provide that as example, and then the computer will learn from this. Right? So now we're, like you can see in this phase where we're doing some meta programming, and essentially the machine learning techniques figure out on their own then what are the instructions that should be followed. And that's how now we've got this, all these breakthroughs that have happened for all kinds of fields. Okay, so here, this is where I would argue that maybe we can think of the singularity as the following, that perhaps it's when we obtain self-evolving computer systems, because what machine learning allows us to achieve now is to have computers that will perform tasks that were not necessarily programmed for initially, but they're just going to learn based on examples, and then they can do new things that even us as humans we could not figure out, or we could not necessarily spell out. Okay, so to be very concrete, let me give you another example. So if we look at AlphaGo, it's been highly publicized, where now it's a computer that can play better than humans, and then so Google designed AlphaGo and then initially trained it by supervised learning, meaning that it took some games from human experts and then provided that as examples, and then the computer essentially learned to play in the same way as the experts. So this is good, but then beyond that, what happened is that there's a second phase as well, where reinforcement learning is used, and now the computer learns to play by itself and learns to play in ways that is not necessarily consistent with how experts would play, and can even play better than human experts. And then so one event that showcases this is, for instance, there was this famous tournament in 2016 between a world champion, Lee Sedol, and then in this tournament there were 5 games. AlphaGo won 4 and Lee Sedol won game. But what's really interesting is that in game 2 there was a very interesting move that AlphaGo did, move 37, where the computer placed a stone right here. And this move, according to the experts, was not a move that would normally be done by people who know how to play this game well. The human odds that somebody would play this move was about 1 in 10,000, so it was not considered a good move. But the computer did that, and then at the time, so you can see Lee Sedol scratching his head, trying to figure out what the heck is that. And then also there were analysts, both on the Korean side, on the English side, making comments about the game, and the initial reaction was like, oh my God, AlphaGo just screwed up, okay? But then everybody started thinking, it's like, what if AlphaGo figured out something, right? And it turned out that this move was in fact a very good move, and then it allowed AlphaGo to win that game, so it completely changed the events in that game, and then it taught something to human experts. So here it was really through reinforcement learning that the computer essentially learned to figure out a new way to play, a way that even the experts had not thought about. Okay, so this is pretty neat. Okay, so today there's AlphaZero that learns entirely to self-play and can even defeat the AlphaGo program that was originally designed by Google, by DeepMind. And yeah, it's been used as well for other games. So now, in terms of developing algorithms to play games, often a purely learning techniques based on reinforcement learning will get us further than simply trying to mimic what experts would do. Okay, so now let's look at more industrial examples. In terms of the singularity, so I talked about how we would like to have some self-evolving systems. So if we just look at telecommunications, so at the moment, everybody is talking about 5G mobile networks, and there the goal is to get about 20 gigabits per second, and also to enable IoT, Internet of Things. But then let's go even further. So some of the leaders in telecommunication are already thinking about 6G networks. And what is 6G going to mean? So the obvious thing would be to say that it's going to be even more bandwidth, but I mean, more bandwidth, so what? At some point, if you can communicate everything you need to communicate, that's not too interesting. And in fact, here, what some of the leaders are thinking about is how this could lead to autonomous, adaptive, intelligent systems that could do some self-diagnosing, self-managing, self-evolution, and then basically, we're going from connectivity to intelligence. And then so here there's a possibility again of a new paradigm based on self-evolution that could lead to a singularity, at least in this market. Yes?
Regarding your definition of self-evolving systems, shouldn't we have a restriction there that this system should have some restriction aligned to the humanity goal of surviving? Yeah. What if this system gets against us?
Yeah. So yeah, absolutely. So here, yeah, there's obviously some important concerns from an ethical perspective, and also making sure that the machines, when they self-evolve, will still remain under our control. At least we'll still do things that are beneficial to humanity. But I guess we're not at that stage yet. So I guess here this is more things into the future. And then the good thing is that most of the researchers who are advancing these technologies are also looking at ways to ensure that this will happen in an ethical way and then for the good of humanity. Yeah. Okay. Okay, so another example, if we look at smartphones, so today when you buy a smartphone, often you're concerned maybe by the battery life, maybe the camera quality, maybe the screen, the size, its resolution, maybe the processor speed, how much RAM, and so on. And then in terms of software features, often you can configure it in a way that's going to be personalized to your needs, and then you can also use various voice-enabled commands, and that's the state of the art, right? But then a lot of the manufacturers now are starting to think that they need to move away from hardware features or basic software features, but then think of the smartphone as like a personal assistant, and then essentially facilitating something that would be more adaptive and maybe even embed in here a self-evolving conversational agent that could assist you with all kinds of tasks and so on. Okay, so yeah, so various people are working on this as we speak. Okay, so now to get this self-evolution happening and eventually singularity as well, there's going to be some challenges. So here I've highlighted 3 challenges. I'm going to talk about the first 2 in more details and show you some advances from a research perspective to circumvent those challenges. But I guess, yeah, we're not quite at a point where a singularity is here, but still, I mean, there's some steps being taken. So I would argue that one important challenge is first that at the moment, when it comes to machine learning that allows adaptivity, that will eventually allow to have self-evolving systems, well, at the moment, the part of machine learning that really works well is based on supervised learning that requires labeled data. So, in various organizations, often this is something difficult where you have some ideas, you'd like to design some new feature that's adaptive and so on, and then you need to feed the machine with data that's labeled that indicates what's the right output, and you might not have that, right? So often there are a team of labelers that will supply this, or otherwise you have to look for new data sources, but basically this is a major bottleneck. So machine learning has enabled lots of breakthroughs, but if we could go beyond supervised learning that requires labeled data, there's actually a lot more that could be achieved. So we really are just looking at the tip of the iceberg. There's a lot more that's possible, but we need to overcome this. Okay, now for self-evolving system, another important challenge is what I would call the ability to bootstrap, where here we would like to be able to have a system that learns, but learns in a way that's open-ended, is not restricted by, let's say, a finite set of parameters or specific hardware and so on, but can be general in terms of learning new concepts and doing new things and so on. And here there's a lot of work to be done to allow this. Okay, and then the last one, robustness. So with all the excitement with respect to deep learning, many of you have probably encountered this, where often those systems are brittle. so they're not quite robust. You can come up with adversarial examples, adversarial attacks that will essentially defeat them. So here, there's a need to essentially design some techniques that will be more robust in that respect, and this will be quite important, especially for self-evolving systems. Okay, so let me talk more in details about the first two, and in particular, for the first one, reducing the need for labeled data. So here, there's already been a lot of work in many years where people have looked at unsupervised and semi-supervised learning, but let me argue that this has not really solved anything. There's another problem where even if you do not need labeled data, you might suffer from what is known as the concept drift problem. So the problem is that if you don't have labeled data that indicates really what's the expected output, then the computer is free to learn whatever it wants, and then it might learn something different than what you're expecting, and in that sense, it will drift away from helping you, and then things might just get worse. So that has been an important problem. That's why unsupervised and semi-supervised learning have not really stepped up to fill in the gap. Okay, so what's more promising, or what are better ideas? So today, there's a new paradigm known as self-supervised learning, so I'll talk about this. There's also transfer learning, where you can essentially transfer whatever you've learned in one domain to another domain, even if you do not have data, at least labeled data. Some people are also looking at techniques to do few shots learning, so how can we learn from just a few examples? And then there's reinforcement learning, where you do not need labeled data, but instead you can just have some weak signal that tells you whether something might be good or not good, but not necessarily optimal, and then you can learn from that. So, okay, so I'll talk about the first two, self-supervised learning and transfer learning. Okay, so as an example, let's consider a vision task where we've got here an image, and let's say we want to just segment the image. So one approach for doing this by machine learning is to do it in a supervised way, where you get somebody to segment by hand, essentially label every pixel, and then train a classifier based on that. But as you can imagine, this is not scalable. Nobody will spend so much time labeling every single pixel. So that's just a no-go, right? So people have looked at other ways of doing this. So one idea, and this is not a new idea, it's been around for a long time, is that now if we don't consider images that are in isolation but as part of a video sequence, then you can leverage optical flow, where at least for moving objects, then the idea is that for segmentation, if you have an object at one location and then it moves to another location in the next frame, and then another location in the next frame, and so on, then all those pixels are going to be moving roughly together. Obviously, it helps if the object is rigid, but even if it's not, then generally speaking, the pixels associated with one object will move together. And then so that gives us already a clue, some information about what are the pixels associated with one object. And then, so there are techniques to measure optical flow, so direction of movements of pixels. And then you can see here, just by computing the optical flow, we already get some good information about people in that scene. So here's another example where somebody is playing tennis, and then you can also get some good information. So here, you can do this in an unsupervised way. Nobody has to label anything. We're simply exploiting information from how we understand that the world works in a physical way, and then we can obtain, from that perspective, the equivalent of labeled data, but without having to pay the price to label it. Okay, so we can do this as well in reinforcement learning. And reinforcement learning itself is another way to also train some machines to be adaptive without having to label anything. And there's an implicit feedback. So in the case of playing some games, so here I've got 3 examples of some good old Atari games. These are benchmarks that are often used in reinforcement learning. And there, the idea is that we can learn a policy that will play well the game. But more than that, I'm going to show you how we can learn a policy that will depend on the moving objects, but instead of training a classifier to segment the objects out based on supervised learning, we're going to do it in a completely unsupervised fashion. So it's all going to be integrated into reinforcement learning, and then so we're going to be able to speed up how learning is done simply by automatically segmenting out the objects. And here the intuition is that to play a game well, right, what are the objects that matter? They're probably the moving objects. They're not always the moving objects. So like you might have, let's say, a bomb or a treasure or something that's static, that's important, but still in many games the moving objects are the thing that matter. Okay, so here what we did is we exploited this notion of structure from motion. There was some work done in the past where a neural network was designed to extract structure from motion. So here's the architecture that we considered. So the idea is that you can have a convolutional neural net that will essentially compute an embedding of the image. And now if you want to extract objects in an automated fashion, then what you can do is simply have a deconvolutional part that will come up with estimates of the location of the objects in terms of some masks, and then based on this compute the optical flow. And then you can have another path here that will also estimate objects' location as well as motion of the objects and the camera. And then if those two are in agreement, then we can train this so that it is in agreement and therefore can automatically extract object location, where the upper part is just regular optical flow computation, does not require any labeling, and then the bottom part will essentially learn to automatically segment out the object, apply some transformation, and then see where the objects are in the next frame, and then compute optical flow and see if this matches here. Okay. So we can do this automatically, and then so here's some examples for one particular game. So this is the game of Breakout, where a player will simply hit a ball that needs to essentially break all of those blocks in the ceiling. And then so in this game, there's essentially two objects that matter that will move. So we've got the paddle as well as the ball, and then we can train using this network here on a sequence of frames in a video, a technique that will automatically recognize the moving objects, so the paddle and the ball. So I guess here it shows where the paddle is. Okay, so this is the estimate of where the paddle is, and then in this case it's where the ball is. So these are object masks, and then here we've got the optical flow, so it shows essentially the direction of movement of the pixels. Okay, so now this game is quite simple, and then I mean the objects are also quite simple, but it's just to illustrate the principle. Okay, so once we have this working, we can embed that into now a technique that will select actions as part of the game. So decide how to move, let's say, the paddle and hit the ball, if this is the game of Breakout, or whatever are the actions for other games. And then, so we start with as input with some images in the video sequence. And then the upper part here is the network that I showed you in the previous slide, where it's automatically segmenting out the objects. So yeah, that's what the upper part is here with the optical flow. But then we feed here the information extracted about where it thinks the objects are and their motion, what's the motion of those objects. We feed that to another network that essentially computes the actions that will be performed by the agent in the game. Okay, so this is a classic actor critique network, but then there's this additional part that feeds in here that provides information about the objects and their location. So the idea is that this will speed up how the agent can learn to play the game, and then it's all done in an unsupervised fashion. So here we did a comparison to some baselines. So two popular algorithms are known as A2C and PPO. When we augmented these algorithms that would correspond roughly to the bottom part, we augment them with the top part that computes object segmentation and location. Then we're able to improve for 26 games. We had similar results for 30 games, and then worse result for 3 games. And then with respect to PPO, these are the results. But now let me show you some videos. In those videos, we've got on the left side the regular interface for playing the game of Pong. And then on the right side, we've got the object segmentation, the object mask that's computed as part of the reinforcement learning technique. And this is done automatically. Okay? So you can see that for Pong, it's doing a pretty good job. It just tracks the objects, feed that to the policy, and then it can play very well, much faster. Same thing for Breakout. So Breakout 2 is just a question of tracking a paddle as well as a ball, so it does it quite well. For Sequest, there's a submarine, and then there's going to be some fish and some divers that are moving, and then it can track those, and then it can do quite well. But then I've got an example here where it doesn't do so well. So Beam Rider, what happens is that there are some beams that just scroll down, that just arrive near the agent. And those beams actually are just a visual feature. They don't change anything to the game. But because they're moving, then the algorithm essentially tracks the beams. And that's completely irrelevant. What it should really be tracking are the monsters and then the bullets that sometimes appear in here. I guess we don't see them at the moment. But okay, here's one, and another one here, and so on. And these are quite small. So now it has trouble to identify them because they're much smaller than the beams. But in any case, it just illustrates that this can work on a variety of games. It doesn't always help, but this is an example of a game where it didn't help. Okay, so here are some examples of some of the results that we obtained. So we've got in yellow and purple 2 variants of the technique that I just showed you. And we can see that here this is the amount of rewards, so how well the agent is doing in the game with respect to the amount of training, so the number of episodes or number of interactions with the environment. So higher is better, and then we can see that the yellow and purple curves are generally higher, so we essentially managed to reduce the amount of data that's needed to train, so it's closer to how humans would play this game. There's obviously a lot of work left to match human performance in terms of playing those games as quickly and as well as humans. But in any case, you can see some improvements for those 3 games. And then for Beam Rider, you can see that the purple curve is at the bottom, so it got worse. Okay, and then the yellow curve is in the middle, so it's kind of not so much better. Okay, so any questions regarding this? Okay. So that's good, so let's keep going. So now I'll switch gears and talk about bootstrapping and then some work that we've done there in terms of transfer learning. So here by bootstrapping, it's this idea that we would like to design some system that can learn some basic concepts, and then from those basic concepts could learn maybe compositions of the base concepts, and then eventually learn compositions of the base concepts, and so on. Just like you see a child would learn some words, eventually can form some sentences, can learn some more complex concepts throughout elementary school and high school, right? So we would like to design some systems that can do this and then can generalize in open-ended ways. So to achieve that, obviously, there's a lot of work left to be done. So there are many steps that have been taken by various researchers. These include non-parametric models that would not be restricted in terms of parameters. Also, lifelong machine learning is another direction. But let me talk about transfer learning, which is an approach for learning something about some concept in one domain and then transferring that to another domain where the concept is related but different. Okay. Okay, so this is some work that I did in collaboration with colleagues at the University of Waterloo in kinesiology. So Laura Middleton, as well as some of her research team. And in this case, we were looking at activity recognition. So it was this problem where, let's say we've got some wearable device that could be a smartphone or a smartwatch. They have some sensors. They might include like accelerometers, magnetometer, also some orientation sensor, and then so they'll produce some measurements, and then from this we would like to recognize what is it that somebody is doing at any point in time, like walking, riding a bicycle, being in a moving vehicle, or running. Okay. Now you could say, well, this has already been done, and you're right. So I mean, pretty much every smartphone today has an app. I mean, there's tons of apps where you can essentially recognize those activities. Now, in our case, the challenge is that we wanted to do this with a different population than just healthy adults or healthy users. We wanted to do this with people who were in stroke recovery. So the idea is that in stroke recovery, people who just had a stroke might be partly paralyzed, and then they need to do more exercise. They need to be physically active in order to rehabilitate as quickly as possible. But then when you've had a stroke, the problem is that it changes completely your life, and chances are, you're not in the mood of doing exercise because it's difficult, it's painful, it's challenging. So we would like to encourage people to do more exercise, and then the idea is, can we get an app that will at least track what activities they're doing and then encourage them to do more activities. Okay? And now it's different than what existing apps can offer, because we wanted to do this with a different set of activities and then also a different population. So you see it's a similar concept but a different concept. Okay, so in this work, initially, because there's already solutions available as part of many apps, and it's well known how to do activity recognition, so we just went ahead, collected some data, initially with 20 healthy adults. The data was recorded over 3 days for each participant, and basically each participant was asked to essentially annotate the data by indicating if he or she was walking, sitting, standing, running, or in a moving vehicle. So here, sitting and standing are not standard activities that are tracked by most apps because there's actually no motion associated with those. But in the case of stroke recovery, it's important to detect those because then they'll tell us whether somebody is sedentary or not. Okay? So right there we had 2 additional activities that we wanted to track. And then for the features, we use something pretty standard. So we simply segmented the data into bunches of 1 second, and then it gave us like 48 features per segment that were based on those measurements. And then we trained all kinds of classifiers that included random forest, support vector machines, neural networks, and then we obtained the following accuracy. So we obtained only 60 to 70% accuracy, which was clearly not good. Okay, so here our colleagues in kinesiology wanted to essentially use the activity recognizer as part of a study, but if we only have 60 to 70% accuracy, it's just not reliable, right? So the question was, how can we improve the accuracy? So here, based on what I described, does anybody have any idea about how we could improve the accuracy? What is it that we could do differently? Okay, so let's pass the microphone.
Wonder what the representation of the test set was in the training set. We were testing for patients who are epileptic. I'm sorry, what did you say?
So yeah, in this case, we
stroke
only
patients,
had healthy adults. So as a first phase, we just wanted to replicate what had been done in many apps with just healthy adults. And then after that, we were going to do it with stroke patients that are in stroke recovery.
Yeah. So I think maybe there wasn't, the training set didn't rightly reflect the testing set. Maybe there were more stroke patients in the testing set or something like that.
Well, so here both the training set and the test sets had only healthy adults. Okay.
Okay.
Yeah.
Then I have to
So Yeah, so that wasn't the problem, but I mean, this was originally, like what you're describing was the problem we were hoping to solve, but we were doing it stage by stage because we just wanted to make sure first that we could get good results on healthy adults, and after that go for stroke recovery patients. Yeah. Actually, let's pass the microphone. Yeah.
Increase the size of the statistical sample, yeah, I mean the number of adults.
Yes, very good. So yeah, here we only have 20 people in our data set. This is very little, right? So yes, we can improve that. So in fact, we did increase that to 50. So this was an important thing to do. Now, there's one additional thing that if you look at this, we should be able to improve as well. Any other ideas? Yeah, maybe just shoot the microphone.
So I guess the examples are pretty biased. You could have the data for non-healthy adults as well.
Well, so here again, we're only trying to do this with healthy adults, so both in our training set and our test set. Obviously, as I mentioned, the end goal is to do it with people who are not healthy, like in stroke recovery, but we were not at that stage yet.
Okay.
Okay. Okay, so he has his hand lifted, so I guess shoot the microphone. There we go. Oops.
Yeah, usually when you have inaccuracies, you want to increase your data rate and maybe the size of your segments.
Right, so okay, increase the data. So yeah, we talked about this already. We could increase the
Well, when I say
data
data rate, I
as
mean
well.
instead of 1 second per segment, you can have
Yeah.
nanoseconds per
Okay, yeah, so we could increase that. So in fact, we did not do that, but this would have been a good idea. Okay, so here I'm looking for perhaps different algorithms here. Can anybody suggest different algorithms that might be better than those three? What is it about this problem that makes those algorithms actually not ideal? Okay, so the microphone is right behind you.
So none of these algorithms have like time dependency, so they don't capture the previous time semantic.
Exactly. So yeah, so here, this is a problem where we've got temporal data, right? So we've got temporal sequences that correspond to, I guess, these different segments. And you see, if somebody is doing an activity at a given point in time, they're likely to be continuing that same activity at the next point in time. So there's actually correlations from one segment to the next, and we should be able to exploit these correlations. Now, none of those algorithms here are exploiting that. All of those algorithms are essentially training by just labeling a segment in isolation from the previous and the next segment. Okay, so then we improved. So we did a second trial where here we increased the number of people to 50, and then we considered instead 3 other types of classifiers. So hidden Markov model, conditional random fields, and recurrent neural network that are all classifiers that are meant to work on sequence data and can exploit these correlations. So we got better results, 70 to 80%, but still, this is clearly not good enough. Okay? So the question remains, what can we do to improve further the accuracy? Does anybody have any additional ideas? Yeah. Okay, so pass the microphone.
So I guess one of the ways you can do to improve your accuracy is by further feature engineering, because right now you basically just extract raw features, which is the raw readings from your all kinds of meters, and you can try to kind of add those together, slice and dice them, and also maybe you can add a sliding window. For instance, you take the most recent like 5 or 10 points, or maybe do some moving average or exponential moving average to maybe that will work.
Yeah, very good point. So yeah, so here feature engineering is quite important, at least historically. This can make a big difference, in fact, an even bigger difference than the algorithm. So, okay, we did not do this, but it would have been a good idea for us to try. So, okay, let me give you guys a hint. So one of my students made the following observation. So we were working with the following regime, where we had in our training set all the individuals except one, and then we're testing on the individual that was left out. And that was the right thing to do, because the idea is that, you see, we want to train something with a classifier with some people, so that then when there's a new person that shows up, and then we can predict or recognize what are the activities that this person does. And then once we would deploy this inside an app, obviously the people that we're going to make recognition for are going to be new people. So we need to make sure that in the test set, right, we have individuals that are different from the training set. So with that, that's the accuracy we're getting. But what is actually more standard in machine learning is the second regime, where what you say is, I have some data, and then I'm going to simply shuffle it, take 90% of it, and then treat it as the training set, and then I will use as a test set whatever is left, so the remaining 10%. But if you do that, and you ignore the fact that some of the data comes from different individuals, then you're going to have essentially 90% of the data from all of the individuals, and then 10% of the data from also all of the individuals. And there, when we do it this way, we actually obtain an accuracy that is greater than 90%. Okay, so here the lesson was that the activity patterns actually differ across individuals. So here, you see, we're trying to recognize activities. Like, let's say I want to recognize walking. Well, the way I walk and the way you walk and the way she walks, we all walk slightly differently, or at least, in the measure and the sensor measurements, the patterns are different. So as a result, if we train on some individuals and we're trying to predict on a new individual that has a slightly different pattern, then there's no reason why it should work well. Okay? So that was the problem. So here, I guess the fundamental issue is the following, that our source distribution for training was different than the target distribution for testing. Okay, so normally in machine learning, there's a fundamental assumption that we make, which is that the training set and the test set both come from the same distribution, so that if you learn something on a training set, it will obviously be applicable on the test set. But if your test set comes from a different distribution, then all bets are off, and then, there's no reason why we should get good accuracy. Right? So this was the problem. So now, given that, does anybody have any ideas of what we could do to address this problem? Okay, so there's a hint in the title. Yeah, okay, take the microphone.
So something I can think about is maybe, again, with the features, maybe added more features like the age of the person or the height or the weight, which can maybe cater the possibility that those are kind of relevant to how you walk or whatever.
Okay, yeah, that's a good idea. So in fact, yeah, we were not using features about the age and the height and things like this, and these could be could help us have input that works in the same way for all individuals. So this is a good idea, but I guess, we did not do this. So, okay, so what we ended up doing is essentially to use transfer learning. So transfer learning is precisely this paradigm where you're learning based on some distribution, but now you're going to transfer, you're going to do something to your classifier so that it actually works on a different distribution as well. But you know that the target is based on a different distribution. So our solution was the following. So here we trained separate classifiers for each individual. So we figured, let's have one activity recognizer per individual. We're going to treat those as base models. So here's one classifier, here's another one for all of our individuals in a training set. And then when we're going to make predictions with respect to a new individual, we're going to try to see how this new individual relates to the ones in our training set, and then simply have a weighted combination of those models. So essentially, you can think of those weights as implicitly identifying who are the closest individuals in terms of patterns, and then assigning a higher weights to these models, and then trying to make predictions based on the models of the closest individuals. So that was at a high level the idea. And then you can think of this as a way of doing personalized transfer learning because we're doing transfer learning at the individual level. And then so for each target individual, we're going to learn different weights like this. And then we're going to be able to leverage whoever seems to be closest, because in a population, even though one individual is different from everyone else, this individual might be close to at least one or a few individual, and then there's a better chance we're going to make good predictions based on that. Okay? All right, so to do this, so this is where I'm going to get a little technical, but yeah, I'll try to at least keep the discussion at a high level. So we use hidden Markov models as our base models. So we had hidden states that correspond to activities. And then the idea is that because it's a sequential model, then we have some transitions from one hidden state to the next, so from one activity to the next. And then there's a parameter that encodes here the transition probability. There's also some features that correspond to the raw measurements or otherwise any engineered features that we might come up with. And then the idea is that in the hidden Markov model, you would simply have a distribution over those features given each state. Okay? So now what needs to be learned is the transition probability here, as well as the parameters of the emission distribution for the features. So here, each feature, I'm going to assume that it's Gaussian. So this is an assumption just for the sake of this example. So if it's Gaussian, then there's a mean and a Gaussian, so a mean and a variance. And then we're going to take a weighted combination of the base models. So that's why we have some weights as well. Okay, so then now at test time, or at prediction time, once we have already learned some base models, then we want to quickly combine them to start making some predictions. So we have another set of weights here that are going to be used to decide which models should be combined with what importance. And then so we formulated this way. So we're going to have two different set of weights, pi and lambda, that correspond to the weights for the transition models. And then lambda are the weights for the emission model. So we're going to combine them in that way. And then that's what we need to learn. So here in terms of transfer learning, so essentially learning pi and lambda. Okay, so to do the learning here, we ended up using a Bayesian learning technique. This is based on Bayes' theorem. It's nothing new. It's several centuries old. But what's really neat about Bayes' theorem is that it provides us with a way to start with some prior. And then based on the data, we're going to update this prior and compute the posterior. But we can do this in an online fashion based on streaming data. So here for activity recognition, this was important because you see, you start making predictions, but at every step, you get more sensor measurements, and you want to use that data to continuously update. So we wanted to be able to learn in an online fashion. Okay, so then Bayesian learning facilitates online learning simply because you start with a prior, then after your first data point, then you have a likelihood, you update the posterior. Then after the second data point, you update again. And so you can update like this one data point at a time. So it's naturally online. It's also distributed if we wish to. So this expression that we need to compute, we can always just break it into several subsets. So we can take part of our data, do the computation with core 1, the other part with core 2, and so on. So in terms of scalability, Bayesian learning, in that sense, is naturally online, naturally distributed, so that's neat. Okay, the trouble with Bayesian learning is that when we do the computation to obtain the posterior, we will obtain something that is not necessarily tractable. So here, we ended up working with products of Dirichlet. So this is the equation for the prior. The likelihood had this form. We obtain a posterior simply by multiplying the prior by the likelihood, and it gives us a posterior, which is a mixture of products of Dirichlet. Don't worry if this is getting a little too mathematical, but the point is that in this mixture, we have a summation that is exponentially large. Okay, so it's not tractable. I mean, we can represent that in closed form. There's no problem in that respect, but computationally, it just gets larger and larger, so the mixture becomes exponentially large with the amount of data. So we need to approximate. So here we use a simple technique where we start with a product of Dirichlet, we do our Bayes update. Normally it gives us a mixture of products of Dirichlet that can get larger, right? So exponentially large. But then before it gets too large, we're going to project that down to a single product of Dirichlet, and then we use a technique known as moment matching for that. So here, very briefly, what I mean by moment matching is this idea that I've got a distribution. Instead of thinking of it in terms of its algebraic form, let's think of it in terms of its moments. So in probabilities and statistics, we can characterize any distribution on some interval uniquely by its moments. And here the moments would include mean, variance, skewness, kurtosis, and so on. Okay? So yeah, we can characterize uniquely. And then in particular here what we did is we have the exact posterior, that's a mixture of products. And then the approximate posteriors would like to have just a single product of Dirichlet. And then we can obtain this approximation Q simply by matching the moments. In this case, we match the means, and then we match the variance. Okay? So it's an approximation, but it can be done quickly and simply. Okay? So that's the approach that we took. Okay, so then this approach, we tried it. We went back to our data set that we had collected with our colleagues in kinesiology. And then so here, this was the original data set with just, 19 people here. And then so what we did is we trained on 18 individuals, tested on 1 individual. And then so here when I write person 1, it means that person 1 was the test person. And then the other 18 people were part of the training set. And then so when we tested on that person, we got the following accuracy. So now you can see that our transfer learning technique ended up beating several baselines that included just a regular HMM trained by Bayesian Learning, as I just explained it. Also, you can train it by expectation maximization, or you can also use a recurrent neural network. So all of these techniques do not do transfer learning. So it's essentially just learning one model to predict what should be done for the future individuals. And then they do not perform very well. Whereas our transfer learning technique tends to work better for most individuals. So here, an arrow going up simply means that statistically the results are better according to the Wilcoxon rank test. Okay, so actually before I move on, any questions regarding this?
So are these still healthy?
Yeah, these are still healthy. Yeah, so now we managed to essentially get good results with healthy people. So unfortunately, no, we did not. What happened is that in parallel with all of this, we realized that collecting data with the patients in stroke recovery was going to be very challenging because the fact that they're partly paralyzed means that they're going to have difficulty operating a smartphone. And then they're often an older population that does not have much experience with operating a smartphone.
Yeah,
so.
What I'm also asking is because I was just wondering, usually with paralytic patients, you're kind of like half paralyzed. So, for example, your whole left side isn't working. But I don't see how it would be realistic to find another person who compares to a paralyzed patient. And I think that would be a bigger challenge. And I was wondering if it would be actually better to actually do the test on their non-paralyzed side and then use that to do the learning and then compare that to their other side. And even in general, wouldn't that actually produce even better results, like personalized?
Yeah, that's a great idea. The fact that, the person is partly paralyzed, there's one side that's still good. But then, okay, if we're looking at activities like walking, unfortunately, you need both sides, right? So a lot of the mobility activities, from that perspective, they still get impacted even if it's just half of one side that is paralyzed. So we did not do that. And in fact, we never ended up doing experiments with stroke recovery patients, mostly because getting data in the first place was a challenge. So in any case, I guess in this talk, I'm just showing you how we ended up at least just going around the problem of a lack of data and also being able to bootstrap. In this case here, it was from one individual to other individuals. But in principle, had we been able to collect data with stroke recovery patients, we could have been able to do something similar. So you see collecting data with on the order of 20 people, maybe 50 people is possible. There's not a large population out there for stroke recovery, but at least it should have been possible for us to do that. And this is where we think that this technique could have worked. Yeah. But okay, now let me show you some results, not just in that context, but then we had another collaboration with some other researchers. In their case, they were interested in sleep stage classification, and there's a similar problem where here they've been collecting data. So they have people who go to a sleep clinic, they put all kinds of sensors while they sleep, and then they record that. So it gives them a polysomnogram. And then the idea is that you want to now segment this into the different stages. So for instance, there's deep sleep, there's also rapid eye movements up here, and then there's other intermediate stages. Okay, and then so this is a classic problem where you want to be able to just identify the different stages. And now, if you want to train a machine learning technique to do this automatically, then you need some labeled data. And then it would typically take a clinician 2 hours to essentially go through a polysomnogram of 7 hours and then do the labeling, segment this. Okay, so you can imagine that this is very intensive, and obviously we're not going to be able to get a lot of data here. And furthermore, the patterns of how one person sleeps can be different of the patterns of how another person sleeps. So we've got, again, inter-subject variability. So the results that are obtained by standard techniques do not work well, but if you use transfer learning, you can obtain much better results. So here we got data from 142 patients at Sunnybrook Health Center. And I've got on the left side here the accuracy for transfer learning, and then the x-axis is the accuracy of some baseline. So here, this baseline is just a regular HMM using the Bayesian moment matching technique that I described without transfer learning. Here it's EM without transfer learning, and here's a recurrent neural net without transfer learning. And then the idea is that whenever we've got points above the diagonal, it means that transfer learning achieves higher accuracy than the baseline. Okay, so at least in comparison to the first two baselines, pretty much every single individual we ended up having better accuracy by transfer learning. With respect to recurrent neural networks, that wasn't the case, but still we had overall still better results. So the majority of the points are above the diagonal. Okay, and then we took yet another problem. This one was in collaboration with Huawei, a telecom company, where in their case, they wanted to predict future flows between two computers. So let's say that you've got a server and a client, and there's an application running, then often there will be flows of data packets that will go from the server to the client, and then back from the client to the server, and then, you know, which flow will go next in which direction is an interesting question, because from a routing perspective, if you can predict what will be the direction of the next flow, then you can allocate resources accordingly and do some better routing. So then, yeah, they just wanted to predict that. And here we can also formulate this in the same way. So there's some sequential data, and we would like to classify what will be at any point in time the direction of each flow. And then, so without transfer learning, we obtain those results, and then with transfer learning, we obtain better results. Okay, so this just gives you an idea that you see transfer learning, as I explained it, can work in a variety of domains. Okay, so let me conclude at this point. So I essentially talked about the possibility of a technological singularity. And here, at least from a machine learning perspective, that might arise in the sense of having some self-evolving computer systems. But then we talked about various challenges. Two important challenges is the reliance on labeled data and also the ability to do bootstrapping. So for labeled data, I explained how we can use a form of self-supervised learning This was in the context of reinforcement learning. We were able to segment out objects automatically. And there's lots of things that can be done whenever we've got interactive systems like this, where we can leverage interactions to automatically obtain information that can train various systems. So if you're interested in this work, this is the reference. This work was just accepted for publication at NIPS, and then we'll be posting the paper shortly on our website. And then the second part of the work on personalized transfer learning, so this was published last year at ICLR, and you can find it on my website, okay? So yeah, so that's what I talked about. But I guess, yeah, there's still a question of will there be a singularity and when? So I don't know, but I would say here that what is certain is that systems are going to continue to gradually become more adaptive and to become more autonomous. And yeah, so I think gradually we're moving towards that. Okay, so let me stop here, and then I can take some questions.
Thanks for that great presentation. We have a little gift for you. Here you
Thank
go.
you.
So to everyone in the audience, thanks for attending, and feel free to stick around. So Professor Poupart is going to be around for a little while to answer any questions you have, and feel free to just network and mingle here in Area 14. So have a great day.